Hi everyone, I'm Kian, and I'm here to talk about the tour of the solar system, or the optimal orbit trajectory to visit as many outer planets as possible. So the tour of the solar system, or as it came to be known as the Grand Tour concept, came about in 1965 when the National Academy of Sciences held a summer study in which they invited engineers and scientists to Woods Hole, Massachusetts to kind of brainstorm what kind of interplanetary missions they could do in the next few years. One of the missions was to visit 4 to 5 outer planets with a single spacecraft using gravity assist maneuvers. They realized that Jupiter's gravity assist could propel a spacecraft to solar system escape velocities. And the reason they could visit so many planets was due to a planetary alignment that occurs once every 175 years, or the same as the synodic period between Uranus and Neptune. Luckily for them, the next window was between 1976 and 1980, occurring every 13 months. Now this mission was very daring and racked up a bill of about $1 billion. On the right you see the 1978 Grand Tour trajectory with flight path angle changes corresponding to the gravitational maneuvers. So the Grand Tour launch window was determined by essentially generating pork chop plots. As you see on the right, there are C3 values as well as launch departure dates and mission duration. One thing they had to consider was not hitting Saturn's rings and destroying their probe, so they had to plan their trajectory so that they would fly within the inner edge or the outer edge of the planet. These trajectories were assumed possible by looking at modern technology and assuming launch vehicles at the time and in the late 70s would have C3 capabilities of between 100 and 200 kilometers squared per second squared. So Jupiter is really handy when you're trying to get out to the outer planets. Because it's so big, it offers such a great change in orbital trajectory and gives you a lot of different missions that you can do. Trying to do direct ballistic trajectories to planets like Saturn and beyond require a bunch of energy and time and can be much more efficient if you use Jupiter as a gravity assist. As you can see on the right, Jupiter fields all of these different missions, the top one being the classic Grand Tour mission. The equation on the left bottom shows the flight path deflection angle as a function of hyperbolic excess speed and the planet's gravitational constant and the closest approach to the planet. The mission designers had to plan for planet ephemeris errors. In 1971, the technology estimates at a 3 sigma confidence interval estimated about 0.4 to 0.5 arcsecond error. However, the Grand Tour mission was suggested to have 0.1 arcseconds of error in planet ephemeris. However, it was predicted that by the late 1970s, when the mission was going to launch, planet ephemeris development would increase in accuracy to 0.1 arcseconds. However, if the ephemeris errors were still too large, the spacecraft was to be suited with an optical planet tracker in order to kind of get the planet ephemeris locally. Now, there were some fast Grand Tour missions that were proposed. These were outside the general 1976-1980 window and omitted a Jupiter gravity assist. They found that they could get to Neptune with a time of flight shorter, 322 days shorter, only requiring a little bit more launch energy. These fast missions extended the Grand Tour window to the mid-1980s, and they realized that a probe on the classic Grand Tour and on the fast Grand Tour would arrive within 1.5 years of each other. So they determined that the shortest mission within reasonable launch parameters to Neptune was actually only 4.5 years with this fast method, including Saturn and Uranus flybys. However, the Grand Tour was very expensive, so NASA suggested the Mariner's Jupiter-Saturn probes. These were 2 probes that were meant to just visit Jupiter-Saturn, and they were renamed Voyager 1 and Voyager 2 as you know them now. Voyager 2 was supposed to be launched earlier. This was because it has a longer flight time than Voyager 1, and this was because it was trying to catch the last little bit of the Grand Tour window in order to get a possibility of visiting Uranus and Neptune. However, this was all contingent on a successful Saturn flyby. Both trajectories for the spacecraft were optimized to pass as many planets, moons as possible. So they launched in 1977, and the Voyager 2 en route to Jupiter actually went silent, and it really harmed their chances at getting to Uranus and Neptune because they needed a very accurate flyby of Jupiter. However, it was fixed, and Voyager 2, as you know, passed Uranus and Neptune and completed the Grand Tour. So, as trajectory analysis software progressed, a lot more Grand Tour windows appeared. In 1991, JPL created an automated mission design tool from some of their existing software. If you put in launch date range, launch energy range, and the sequence of target planets you want to see, it will examine all the trajectories involving these target planets. So analysts ran this tool with a variety of parameters, a time of flight of less than 7,500 days, a V-infinity of less than 12 kilometers, and they ran it between 1965 and 2180 with a step size of 20 days. This resulted in the traditional expected windows between 1967 and 1982, and then 175 years later, starting at 2153. Other simulations resulted in a 1996 launch window for an alternate grand tour of Jupiter, Uranus, Neptune, and Pluto, with a little bit more launch energy and time of flight. So there definitely were some limitations because it used approximations and assumptions. The tool used conic sections by solving actually Lambert's problems between each leg of the trip. Each gravity assist assumed impulsive maneuvers and had to sufficiently bend the V infinity of the vector. Now the tool couldn't quite predict precise arrival times. These could be calculated with more sophisticated methods, but they decided that it wasn't significant. You know, a few weeks off at Pluto wasn't significant in a 2-decade or even 1-decade-long mission. So JPL designers found that it was patch conic was sufficient for gravity assist maneuvers in modeling the orbit trajectory. So the JPL tool's data was a lot more sophisticated than in the 1960s and 70s. You can see on the right the influence of V-infinity on your launch opportunities. Of course, if you have a better rocket that can take you further, you can obviously go more places and your launch opportunities are wider. An interesting thing is that JPL allowed subsurface flybys in their analysis. They believed that it was useful in studying trends, so they'd set their lower bound to negative 1,000 kilometers altitude when the spacecraft was performing its flyby. However, when the mission was more refined, these would be updated. So the tool also spit out recent and future windows. It showed us that Jupiter can be paired with a lot of the outer planets every 13 years. And we have a couple 3-planet opportunities in the 2030s that we might be able to send probes to. So with Voyager 2 completing its mission and completing the Grand Tour, as well as New Horizons grabbing that straggler picture of Pluto, it didn't seem that any more Grand Tours were necessary. We got kind of the general flybys of the main planets in our solar system. So now NASA missions are mostly focusing on single planet missions and exploring their moons, as well as looking to Mars due to frequent optimal trajectory windows and that it's so similar to Earth. However, Grand Tour inspired missions really exhibited to the astronautical community the practical uses of the gravity assist maneuver and how we can use it in the future. And it also helped advance the multiplanetary orbit optimization and trajectory analysis of orbit determination software. Thank you.